Hello, physics students. Today we're going to summarize what we know about work and energy. As we mentioned before, we view energy as something that is necessary in order for a system to have the capacity to change. Now, to add energy to an object or system, work must be done. Specifically, work adds mechanical energy. Now, to add energy, we do work. The equation for work is work is equal to a force parallel to a distance being moved. And this is a key idea. If an object does not move, then no matter what force you apply to it, no energy is getting added to that object. Now, often this is rewritten as a force times cosine of an angle times the distance being moved. And often the distance is moved to the front, so it's not confused to be an argument to the trig function. That is, in your head, you should think of this diagram. If I have some object being moved and I push that object at an angle, and I'm moving in the same direction as that force, only the part of the force that actually is in the direction of motion, that is the x component of the force, which in this case would be equal to F cosine theta, which is where the angle is coming into the work equation. So key thing is both the force and the distance moved must be in the same direction for work to be added, for work to add energy. Now, work adds energy. So as I add energy, that energy can be added in different forms. I have kinetic energy, the energy of movement. That equation is kinetic energy is equal to 1/2 the mass of an object times its velocity squared. All these energy and work are both examples of scalar quantities. Although velocity is a vector, when I calculate the kinetic energy, I'm calculating a scalar quantity. Same with work. Technically, this is known as a dot product, a way of multiplying two vectors, force and displacement, to create a scalar. So one type of energy the work can add is kinetic energy. Another energy that we can add is gravitational energy. Now, gravitational energy is energy stored in a gravitational field. That is, when I do work on an object, I lift an object against the force of gravity, I am storing energy in the gravitational field. Now, often we simply consider this. We often will simplify this as saying that gravitational potential energy is an energy caused by a change in position. So we can write that equation as gravitational potential energy is usually calculated with the mass times the gravitational acceleration g, 9.81 on our planet, times a change in height. Now, it is that change in height that matters. Only a change in potential energy really is useful to us. And so often, though, we'll define the lowest height of a problem to be 0, and then we'll rewrite this change in height as simply just h height. And then finally, elastic potential energy. Elastic potential energy is what happens if you stretch a spring. If I have a spring of some stiffness k, which again is just a number that describes how difficult it is to stretch the spring, and if I then pull on that spring some distance x, that is, I stretch the spring out by pulling on it, then the elastic potential energy stored in that spring is equal to 1/2 the spring constant times the amount you stretched it squared. Now, we will talk about energy from a changing force like a spring a little bit later, but this is energy stored in a spring. Now, the big idea is these energies do not have to stay in one form. If I roll up a hill, then my kinetic energy may turn into gravitational potential energy. If I push against a spring and then let it go, then the object might gain kinetic energy, or I'd later roll up a hill. So all these energies are transferable into one another. So the total amount of energy you have, the kinetic energy plus the gravitational potential energy, plus the elastic potential energy, this total amount of energy for an object must be conserved. That is, the total cannot change. And so this is the big idea of physics. Without something taking the energy away, that once an object has mechanical energy, it will keep its mechanical energy. Although that mechanical energy is free to change form. I can take kinetic energy and change it into potential energy and vice versa. Now, we'll see an example of this in the next video. Now, what takes away energy? What takes away energy is negative work. So positive work means I gain energy. Negative work produces a loss in energy. Negative work is mostly done by friction. So if I have an object and it's moving to the right with some distance d, the force of friction is an example of a force that always acts in the opposite direction. If an object experiences a force opposite the direction that it's moving, then that force is doing what we call negative work, and it actually removes the energy. Now remember, the unit of work would be equal to a Newton times a meter. But since it adds energy, we know that 1 Newton times a meter is equal to 1 joule, abbreviated J. All right, so positive work, that is the part of the force in the direction that I'm moving, will add mechanical energy. That mechanical energy can be in the form of kinetic, gravitational, elastic, and once you give an object energy, it holds that energy unless something like friction or another force is opposing that movement, which would take away energy. Now, the rate at which a force does work is called power. Power is equal to the work done on an object divided by a change in time, or often we'll say that this is a change in energy over a change in time. For power, that unit would be a joule per second, and 1 joule per second is known as a watt. A watt is a unit of power. Now, there is a special case of the power equation if you're moving at a constant velocity. Special version. So in that case, the power equation has a special equation where power equals the force times the velocity traveled, right? Where V is equal to a constant. And of course, that means the force must also be constant. So when an object is moving at a constant velocity, there is a special version of the power equation where the power is equal to the force acting on the object times the velocity. But this is only useful when the object is moving at a constant speed. That is, you are pushing just hard enough to cancel out friction, or perhaps you're pushing an object up a hill and the weight of the object is working against you. So again, it's a useful equation, but understand its constraint. This is only when the velocity is constant. You cannot use this when the velocity is changing. If the velocity is changing, then we use the general form of the power equation. Power equals work divided by time. I hope you found this summary useful. Next we'll look at a couple of problems.